Welcome to my presentation about t-tests and how to perform t-tests in IBM's statistical software SPSS. My name is Brian Ortega and I'm going to be talking about the following things. A quick overview. First, I'm going to brush up on z-tests, which is just a leeway into introducing t-tests. For every t-test, we're going to go through the assumptions that are necessary in order for them to work, as every t-test has their own unique set of assumptions that are made in order for them to work. We're going to go through the 4 different types of t-tests, also including a brief explanation of the z-test. We're going to go through the one sample t-test, the student's independent samples t-test, Welch's independent samples t-test, and last but not least, the paired samples t-test. After going through the different kinds of t-tests, we are going to have a few examples of these, not all, but 2 t-tests on IBM's SPSS software. The examples are going to be the one sample t-test and the paired samples t-test. So you may be wondering what t-tests are and why they are necessary in statistics. A lot of the times in statistics or in research, you come across a scenario where you have to compare 2 different means. And you may be thinking, well, that's not a problem because we can simply take chi-square and compare the different results to see if they're significant. Or you may be thinking of just taking the difference between the 2 means and seeing if there's a difference at all. While yes, in essence, this is essentially what we're doing when it comes to t-tests, but t-tests take care of the many different things that we have to take into account in order to make precise statistical calculations. When it comes to z-tests are simply the sample mean, which we can see here on the equation that I included on the screen. It's the sample mean x bar minus the population mean that is predicted by the null hypothesis mu naught. And this is essentially the mean that we're comparing the sample mean to. Anyway, so it's x bar minus mu naught all over the standard deviation sigma divided by the square root of the population mean n, or the sample size n. A few things that we must assume in order for the z-test to work. First, we must assume that the data is normally distributed, and when we bring this up, we are referring to the fact that the data is distributed on a bell curve. And this is a very common thing to assume when it comes to t-tests. Second, we must assume that the data being compared is independent or random, which is near impossible to achieve, but that doesn't mean that we can't do anything to minimize this. There are many things that one can do to minimize, and this simply means controlling the actual research. And finally, we must assume that the standard deviation, which is sigma in this case, has to be known and the same for both the true and the sample population in order for the z-test to work. Now this is where the problem arises when it comes to z-test, because this last assumption is always wrong. If our hypothesis is trying to find whether the means of the 2 groups are different, then why can we assume that the standard deviations are the same? It's simple, we can't. Essentially, the z-test downfall stems from the fact that we're relying on an estimate for the standard deviation of the population. Now, all hope isn't lost, because this is where the t-test comes in, essentially making up for the fact that we have to rely on an estimate. We now introduce the one sample t-test. The only difference between the z-test and the one-sample t-test is that we're essentially acknowledging the fact that we do not know the true population mean, and hence we're working with the estimated deviation for the specific sample. This gets rid of uncertainty because we're no longer assuming that we know the true standard deviation for the population. The effect that this ultimately has on the calculation is that it makes the statistics more resemblant to that of the sample, but it also changes the data from being normally distributed to being t-distributed, or essentially having heavier tails. One thing to note, as the number n, which is the number of instances of the sample mean or the sample size, as the sample size n increases, the more resemblant of a normal distribution the data will have for these t-tests. Once again, just to highlight and reiterate, the only real change between the z-test and the one-sample t-test, as we can see here on the t-test formula, is that instead of an estimated or a standard deviation that is assumed to be known, we are simply acknowledging the fact that we're using the sample standard deviation instead. In order for the one sample t-test to work, we make all the same assumptions as the z-test except for the last problematic one, assuming that we know the standard deviation of the true population. This is where, once again, the difference is found between the z-test and the one sample t-test. Once we acknowledge that we are using the estimated deviation of the sample, the one sample t-test is perfect for when we want to compare the mean of a group against a standard value. For instance, let's say we have a study regarding height in males, and this is a long-term study for a new growth hormone that has recently been rolled out. Wanting to see if the new hormone produces any statistically significant results, we can use the one sample t-test to compare the growth of the people that are using the new hormone versus the national height average for males, let's say. Now, you might be thinking, in the real world, we are always conducting these kind of comparisons. What if we want to compare different variables in a study utilizing the same sample group? Well, now we introduce the independent samples t-test, or more specifically, the student's independent samples t-test. So, the student's version of the independent samples t-test. This test is called the student t-test because back in 1908, William Seeley Gossett figured out how to compare two different populations more precisely. But at the time he worked for Guinness, and Guinness believed that this kind of statistic calculation was a trade secret. Hence why Gossett went ahead and published everything under student. Funny little anecdote. But regardless, as was briefly mentioned, the independent samples t-test, or the student t-test to be more specific, is perfect for when we are comparing two groups from different populations within a study between subjects. Or to put it in other words, we want to compare the results of different conditions within a study, where each group represents a different condition. In terms of hypotheses, which I have up here in the top right corner of the screen, when it comes to our null hypothesis, let's say mu1 equals mu2. This is representing the means of the first population, and it's saying that it's equal to the mean of the second population. Essentially, by saying this in the null hypothesis, we are saying that there is no difference between the conditions. Now, when it comes to our alternative hypothesis, if we say that the mean of the first sample group is not equal to the mean of the second sample group, then we can say that there is a potential significant difference between the conditions. And once again, in this case, mu1 represents the true population mean for group 1, and mu2 represents the true population mean for group 2. When thinking about how to construct this calculation, we have the comparison between the two sample group means and divide it by the standard error. To achieve this, we must get a pooled estimate of the deviation of the sample. So essentially, we're left with the student t-test being the difference between the sample means of group 1 and group 2, as we can see here, all divided by the standard error of this difference, and the standard error being the pooled estimate of the standard deviation, which we can see right here, times the square root of 1 over the sample size of group 1 plus 1 over the sample size of group 2. A few assumptions must be made in order for this test to work. First, we have the common normality within the t-test. Second, we also assume that the two groups are completely independent and that the participants or data points do not overlap in any way. So, for example, we cannot have a participant taking part in a before and after research study, because then this independent samples t-test would not be suitable. A instance that would work is a research study where every participant is strictly assigned to a single condition. The third assumption is what makes the student t-test relatively easier compared to the next t-test that I will bring up, but it is also a slightly flawed assumption. We must assume that the population standard deviation is the same in both groups, or in other words, there is a homogeneity of variance. This problem is similar to that of the z-test. If we don't assume that the two groups have the same mean, then we really shouldn't assume that they're going to have the same standard deviation. Now, we can't always assume this with every study, hence why we have the Welch's independent samples t-test. When it comes to the Welch's independent samples t-test, the main difference arises in how the standard error is calculated, because other than that, it has the same setup where the difference between the sample means are divided by the standard error, as we can see right here, and the standard error of the same difference. But as previously mentioned before, the problem with the student's independent samples t-test is that we cannot assume that both of the sample groups are going to have the same standard deviation. So we must use the specific standard deviations for every group when it comes to calculating the standard errors. So rather than multiplying the shared standard deviation into the square root of 1 over the first group sample size plus 1 over the second group sample size, we utilize each individual standard deviation, as can be seen right here, with 1 and 2 denoting which sample group they refer to. So the standard error is the square root of the standard deviation of the first sample group divided by the sample size of the first group plus the standard deviation of the second group squared. Do not forget to square both of these. So the standard deviation of the second group squared divided by the sample size of the second group. That is going to be your standard error. And essentially, by utilizing the specific standard deviations for each sample group, this provides a more accurate standard error of the difference between the two sample means rather than trying to estimate a pool standard error. The other difference between the Welch's and the student test, the t-test, independent samples t-tests, also arises in the degrees of freedom. Whereas for all of the other t-tests, this is really the only t-test where the degrees of freedom is a little different. All of the other degrees of freedoms is simply the sample size minus the conditions or constraints, the amount of conditions or constraints. And a lot of the times it's going to simply be n minus 1. But in this case, the degrees of freedom is generally the samples, the first sample group's standard deviation squared divided by the first sample size plus the second group standard deviation squared divided by the second sample size, all of that squared over the first sample group's standard deviation squared divided by the first sample group sample size squared divided by the first sample size minus 1 plus the second sample group's standard deviation squared divided by the second sample group sample size squared divided by the second sample size minus 1. Some of the assumptions that we must make in order for this test to work includes assuming that the data has a normal distribution, once again. Second, that the two groups are independent, just like in the student's samples t-test. We must assume, and this only works for studies where the groups are independent. There is no cross-participation in any way. And we no longer have to assume homogeneity of variance. We no longer have to assume that the two groups have the same standard deviation, which is why the Welch test is more widely used than the student's independent samples t-test. The Welch test is perfect for the same scenarios as the student tests. Okay, but what about when we have some cross-testing? For instance, a research study where the participants do both conditions, or the groups come from a single population. Let's say maybe you're testing a before and after condition, maybe before medication and after medication, or let's say we're running a study where we want to see if studying with music has any effect as opposed to studying without music, comparing the two performances. These are just a few examples. This is where the paired samples t-test comes in handy. The paired samples t-test is essentially just a one sample t-test, but run on the difference between the groups/conditions. So in the instance where we are running a paired samples t-test, we create another set of data that consists of the after condition minus the before condition, and that's this right here. And we do the after minus the before condition if we want the progress to be positive. But now that we have this new set of data which is resemblant of the difference between the before and the after, we compare the difference mean to the difference of 0 because our null hypothesis will be that there is no difference arising from the condition, meaning that mu1 of the difference, or mu of the difference, is equal to 0. Now, the alternative hypothesis is going to be the opposite of that. With this in mind, our t-test ends up becoming the mean of the difference, which is represented by d bar right here, over the standard error of the difference, which turns out to be the standard deviation of the difference over the square root of the sample size. As for assumptions for the paired samples t-test, it is going to be the same as the one sample t-test, except for the groups being independent because the participants are doing both conditions. And we all, of course, we are going to be assuming that the data has a normal distribution. Now we get to IBM's SPSS. Now what does SPSS stand for? SPSS stands for Statistical Packages for the Social Sciences, and SPSS is essentially just a statistical software platform Very similar to R, but it has its own different functions and quirks. This software actually looks very similar to Microsoft Excel, where both are very powerful and provide quick answers, but SPSS is designed for statistics. It provides a user with an easy-to-use interface, and paired with its quick calculations, it gives it a quick and easy way to use the program that provides more complicated statistic calculations. SPSS is capable of extracting data from Excel files like .xls, .xlsx, or .xlsm. Today, I am mainly going to focus on how to transfer data from text files, more specifically from xl.csv files. First, the data has to either be delimited with a character or be formatted vertically with fixed width. These are the two patterns that SPSS looks for when it comes to differentiating between different data sets and points. Given that we are already using a .csv file, this means that the data is already delimited with commas. The only thing we have to make sure is that the first row contains the different data variables. Although this isn't completely necessary, this is ultimately the easiest way for SPSS to interpret your data. Once we ensure that our .csv file looks very similar to the example that I have provided right here, we can start the process of actually transferring the file into SPSS. So the first thing that we're going to do is we're going to open SPSS. And once SPSS is open, we're going to press File, Open, and then Data. This will open a new window where you will select the data that you want to import. In the File Type drop-down menu, select .csv. Once we make sure that we have specified that we are going to be using a CSV file, we're going to change the directory to the directory in which the data file is found. Then we're going to select the file, and finally we're going to press Open. This is me selecting the data that we are going to be transferring, and this is what comes up after you press Open. In this window, this will begin to walk you through the transfer process. We want to make sure that the preview matches the data that you're trying to transfer, and as for the predefined format, most of the time we can leave this at no. This little detail comes in the very last step of this text import wizard, but unless you're going to be importing a lot of data that has a similar format, it's not really going to matter as much. This is simply the window where you select which format you want to process your data as, and that's just going to skip through a few more windows. You can continue and press next. And on this next window, since we are transferring a .csv file, we can set the first option to delimited. Then, assuming we included variable names in the first row, we could put yes for the second option and specify 1 to indicate that the names are in the first row. Press what character is used to indicate a decimal and press next. Then it is going to ask where the first case of the data starts. On this window, it's going to ask where the first case of the data starts, and this is simply referring to what row on your excel.csv file the data begins on. And unless the data starts somewhere other than on the second row, specify which row. Well, specify which row regardless, because I do know that sometimes when using Excel spreadsheets, it is convenient to not put sets of data in the top left corner. On this window, it's going to ask about differentiating between the data points. And again, since we're working with .csv files, the delimiter is a comma. Right below, we're going to specify whether there are any leading or trailing spaces from string values and whether they need to be removed or not. In this window, we are simply specifying the format of the data that we are working with, and this could be dollars, dates, numeric, and all of this we're going to be selecting from the data format menu that's down here. And we can also change the name of the variables. And we want to make sure that we do this for every set of data that we have in the data, I guess, or the different groups. Now in this last window, as I mentioned before, it's going to ask if you want to save the format of the text file to skip a few steps next time you import similar data. And once again, this would apply in the first window that pops up next time you import data. You can press finish if you don't need to, or you can press finish if you would like to. But then this window will pop up once you press finish. Now don't be frightened. This window that you're looking at right now, this is simply the window where your statistics are going to be outputted. So any tests that you run on your data, this is the window that your statistics are going to be outputted on. To get to your data, you simply want to press this button right here with the star. Now that I showed you guys how to transfer data from a .csv file, we're going to do two examples that should feel very familiar. I'm going to be reusing the datasets that we utilized in this class for homework 4 to demonstrate how we could have achieved these analyses in SPSS. One thing to note is that SPSS has two windows now, and the star button simply took you to the window / tab that contained your data. I briefly mentioned this in the last slide. Being in the window where your data is located, you want to click on the Analyze tab and scroll down to Compare Means. And then you want to select the appropriate t-test. For this specific instance, we were essentially tasked to compare daily sales from a subscription warehouse store, much like Costco or Sam's Club. The only thing is that they're considering on implementing a discount program, and they are going to try it for a week and keep track of the sales from the week before the discount program is tested and during the week that the discount program is tested. Given that we want to compare two means from two groups, we can either choose an independent samples t-test or a paired samples t-test. Taking into consideration that the people shopping at these stores have most likely shopped both before and during the discount program test, we're not able to assume group independence, hence why the paired samples t-test is more suiting. Now, we're going to click on Analyze, go down to Compare Means, and select Paired Sample t-test. A new window pops up. Now on this window, we're simply going to drag the groups into the paired variable section. We can do this by dragging the sets of data or by clicking on the set of data and then pressing the blue arrow. For this test, we're just going to leave everything else the same and press OK. Now this is automatically going to bring up a report. And keep in mind, as I mentioned before, that this report is on the other window that is the one besides the window with the spreadsheet containing your data. On this slide, I concatenated the information that is displayed so that it fits on the slide. But from the information, we can see that the standard deviations are indeed different. Given that we are simply looking to see if there was a significant change between the groups in either direction, we consider the two-sided p-value. Looking at it, we have a two-sided p-value of 0.040. This means that it is statistically significant. So to put it all together, after running the paired samples t-test, the t-test returned an average increase in sales by $50.38 with a t-test statistic of 2.61 and a p-value of 0.04. Since the p-value is less than 0.05, this is statistically significant, and therefore I would say that the discount program has increased sales. Now let's do another example using the drink sugar data set from homework 4. A little bit of context for this drink sugar data set. A shop that makes smoothie drinks uses a recipe for its banana smoothie drinks in which the drink is supposed to contain 10 grams of sugar. The drinks are produced by a special machine that adds the sugar in a container before it mixes everything. An employee is suspicious that the machine does not add 10 grams of sugar for each drink. If proven right, the machine must be replaced. And we tested the sugar levels for 25 drinks. Once again, we transfer the data from the smoothies. Once again, just going to the text import wizard, making sure everything is lining up in the previews, everything's transferring correctly, specifying where our data is, specifying which delimiters are between the variables, managing variable name, data formats, and we're not going to be saving this file format for any future use. We now go to the data which is now presented on the window here, and we start to do the analysis. Now in the case of this scenario, we are comparing the mean of the sample population to a standardized value, which in this case is 10 grams of sugar. Considering all of this, the most suitable t-test would be the one sample t-test. We select one sample t-test in the Analyze menu. This window pops up, and as before, we simply select the data that we want to analyze and put it into the test variable section. But before we press OK, this little input box that is down here, the test value, this is going to be the value that we are comparing the sample mean to. So in this case, we are going to put 10 inside of the input box because we need the smoothie machines to put 10 grams of sugar in each drink, and we want to see whether or not it is doing this precisely enough. We press OK, and the window containing the statistics should come up once again. And this is just making sure that we set the test value, or the value that we're comparing to, is set to 10. After pressing OK, the window that contains the statistics comes up once again. Now looking at the information in front of us, we can see that the 25 drinks that we tested have a mean of 9.986 grams of sugar, with a standard deviation of 0.0341. The t-value came out to be 2.021 with 24 degrees of freedom. Once again, we're looking at the two-sided p-value because we're curious as to whether the machine puts exactly 10 grams, less than or more than 10 grams of sugar in each drink. Taking this into consideration, we see that the p-value is 0.055. Hence, the mean sugar for the 25 smoothies was 9.986 grams of sugar with a standard deviation of 0.034 and a two-sided p-value of 0.055, along with a t-statistic of 2.021. Because the p-value is greater than 0.05, this means that the null hypothesis must be accepted because the results are not significant enough to reject the null hypothesis. This means that every smoothie has pretty much 10 grams of sugar, and the smoothie machine should not be replaced. Thank you guys for watching my presentation.